Hi everyone. Today we would like to discuss about the canonical LR parser and the look-ahead LR parsers, the two most powerful LR parsers among the LR parsers what we are going to discuss. Earlier we have already discussed about the SLR parser, which means the simple LR parser. Though it seemed to work well among most of the context-free grammars, yet there are few context-free grammars for which SLR parser leads to multiple entries. The study says that SLR parser produces parsing tables for unambiguous grammar, and it has been found that all SLR grammar is unambiguous, but every unambiguous grammar need not be an SLR grammar. What do you mean by an SLR grammar? Any context-free grammar which produces at most one entry in every cell of the SLR parsing table is termed to be as SLR grammar. There are certain context-free grammars for which SLR parsing table will have more than one entry in a particular cell, and therefore those grammars, even though they seem to be unambiguous, they are not SLR. That when there are multiple entries in a SLR parsing table, it might lead to the shift-reduce conflict and the reduce-reduce conflict. What do we mean by a shift-reduce conflict? Either we shift an input character from the input stream onto the stack, or we try to reduce the content of the stack. Which am I supposed to choose? It is not deterministic. And then there is one more conflict which we call it as reduce-reduce conflict. Even in the stack content, we'll be able to identify two different substrings which can be reduced at a particular point of time. Which one are we supposed to reduce is again a question. If these two conflicts are there in an SLR parsing table, the parsing of a given string or the parsing of a program or the code snippet is going to be tedious, and therefore we go for powerful LR parsers. Now for example, we would like to take the example of a context-free grammar where you have S produces L equal to R, S produces R, L produces star R, L produces ID, and R produces L are the various productions. As per our SLR algorithm, finding closure of S dash produces dot S, the augmented production, leads to the first item set I naught from S dash produces dot S, which leads to the inclusion of the next two productions, S produces dot L equal to R and S produces dot R. Because you have dot and L after it, we will be including the next two productions, L produces dot star R and L produces dot ID. And because of S produces dot R, we are supposed to include R produces dot L. Now the goto function for the item S dash produces dot S on S leads to item set I1. Let us take a closer look of the item set I2. Item set I2 has been produced because of the movement of the dot over the non-terminal L. When we check the item set I0, we have two items, S produces dot L equal to R, and the next item L produces dot star R, the last item R produces dot L. Both these two items have L after dot, and therefore goto of I0 on L will lead to S produces L dot R, a movement of dot one step ahead equal to R, and R produces dot L. Now let us consider this item set I2. Item set I2 has a go-to production as well as an completed production. S produces L dot equal to R will have an go-to function on equal to. If it has an go-to function on equal to, go-to of I2 comma equal to leads to I6. Whereas R produces L dot is a completed item which does not have an go-to function. Rather, it has an reduction function. Now, what do we do while reducing? We are supposed to do an reduction entry for the follow symbols of R. So, what is the follow symbol of R? Follow symbol of R would be equal to an dollar sign based on the rules of follow. Now, I have to place an entry of reduce by R produces L under equal to and dollar sign, and if you remember, go to of I2 on equal to is I6. So I2 on under equal to will have two entries. One is shifting to item set I6 and the other one is reduce by R produces L, which has an reduce or an shift conflict. That is shown in the parsing table. So we have a multiple entry, and when the top of the stack on parsing is 2 and we read equal to, the parser cannot make a decision whether to shift the next character or to reduce based on the production or produces L. There is another example which talks about an reduce conflict. Now here we have a grammar where with 4 productions, S produces A, B and S produces B, A produces epsilon and B produces epsilon. On finding closure of the augmented production, S produces S. The item S produces dot S has been included. Because we have S after dot, the other two items which starts with S has been included. Here you have dot A and dot B. The item of A produces epsilon would be A produces dot, and the item of B produces epsilon is B produces dot, which has been included. Now take a look at the items from item set I0. The first item has an go to function on S. The second would have an go to function on A. The third would have an go to function on B. Talking about the other two items, A produces dot and B produces dot, we'll have to reduce based on this production A produces epsilon, and we'll be able to produce based on the production B. Now to make an entry of the reduction based on A produces epsilon and the entry based on reduction based on B produces epsilon, we are supposed to find follow of A and follow of B. Follow of A from this production, for A is followed by small a and A is followed by small b. Therefore, follow of A is A and B. Similarly, follow of B is B and A. Therefore, you will have multiple entries under A and B saying it to reduce based on the third production as well as based on the fourth production, which is again an reduce conflict.